This module introduces a popular kind of static analysis called type systems. Type systems are often specified as part of the programming language and built into compilers or interpreters for the language. The main purpose of a type system is to reduce the possibility of bugs by checking for logic errors. A common example of such an error is applying an operation to operands that does not make sense, such as adding an integer to a string in a Java program. A type system checks for such errors using a collection of rules, which assign types to different parts of the program, such as variables, expressions, and functions. We will learn about the notation for type systems, various useful properties of type systems, and how type systems can even be used for describing other kinds of static analyses. Type systems are the most widely used form of static analysis. They are used in nearly all mainstream programming languages. One reason for this is that they are widely recognized as being important for maintaining the quality of programs. Let's look at an example of the kind of errors that a type system typically catches. Consider the following Java program, which defines a function f in class T in a file named t.java. When we compile this program using the Java compiler, it produces two type errors. The first error states that the if condition on line 4 expects its argument a to be of type Boolean, but it is instead of type float. The second error states that the return result C of the function f on line 7 is expected to be of type int, since the specified return type of function f is int, but it instead has type integer array. Java's type system prevents logic errors like these, which could cause the program to produce undesired results. Besides being a static analysis in their own right, type systems also provide notation that is useful for describing a variety of different static analyses, such as type checking, data flow analysis, symbolic execution, and more. To discuss type systems, we must first ask ourselves, what do we mean by a type? It is easy to label the number 2 an integer and the number 1.125 as a floating point number. But it isn't necessarily obvious how to define what a type is. To put it simply, a type is a set of values that constitute that type. For example, in Java, the type int is the set of all integers, at least those integers that can be represented in 32 bits of data. The double type is the set of real numbers that can be represented in a certain 64-bit IEEE standard. And the Boolean type is the set consisting of the values true and false. Moving away from primitive types in Java, we can come up with more complex examples. If we have a class named foo, then the foo type is the set of all objects of class foo. List of integer is the set of all list objects which contain integer objects. Note that list is a type constructor. It can be treated as a function that takes one type, in this case the integer type, and maps it to another type, in this case the type of lists of integers. We can also have function types. For example, int arrow int is the set of all functions that take an int as their argument and return an int as their result. Some examples of functions of this type would be the increment operation, a function that squares its input, and many others. Abstractions are an integral part of all forms of static analysis. Recall that in data flow analysis, we abstract the control flow of programs, and in pointer analysis, we additionally abstract the heap by lumping together objects allocated at the same allocation statement in the program. Why do we do this? The reason for abstracting program properties goes back to the undecidability of static analysis. We cannot reason directly about the infinite set of all possible concrete values. If we tried to, we have no guarantee that our analysis would terminate. Additionally, even for finite sets of concrete values, abstraction allows us to improve the performance of our analysis. The abstractions used in type systems are the types themselves. Each type represents a large, possibly infinite set of concrete values. By abstracting away these large sets, we enable ourselves to reason about the values based on properties they have in common. A type is an example of what is known as an abstract value, in that it represents a set of concrete values. The Java type int represents all integers representable with 32 bits, and the list type represents the set of all list objects. In type systems, every concrete value must be an element of some abstract value. Therefore, every concrete value has a type. Now that we have a better understanding of what types are, we will learn how to compute with them. That is, how to actually analyze programs using type systems. Type systems have a well-developed notation for expressing these sorts of analyses. In fact, a major part of defining a type system involves defining a set of rules showing how to check that a given program has a given type. In the next lesson, we will provide the notation for type systems, which consists of a set of rules that can be used to check that a given program has a given type. Later on, we will discuss important properties of type systems, including how to infer the type automatically for a given program. Finally, we will see how to use the notation of types to describe other static analyses. Let's introduce a simple typed language based on the Lambda Calculus. We will use this language to provide concrete examples for the abstract principles of type systems. Each expression in this language ultimately evaluates to one of two kinds of values v. Integers, denoted here by I, but which may be any integer value, and functions, denoted as follows. Lambda x of type t yields e, where x of type t is represented by x followed by a colon followed by t, and yields is represented by an equal sign followed by a greater than sign. This notation means a function which takes an argument x of type t and returns the result of computing expression e. Both kinds of values, integers and functions, can be stored in variables denoted by x. Other identifiers may be used for variables as well. The plus operation requires that both e1 and e2 be integer valued expressions. Our type system will ensure that this requirement is indeed met in all executions of a program in this language. In other words, that e1 and e2 can never evaluate to a function value. Similarly, this operation denotes a call to a function e1 with argument e2, and there is a similar requirement on the kinds of values that e1 and e2 might evaluate to. Our type system will also ensure this requirement. To meet these requirements, the system consists of two kinds of types, corresponding to the two kinds of values in our language. An int type, which is the type of all integer values, and a function type, denoted t1 arrow t2, where the arrow is represented by a hyphen followed by a greater than sign. which is the type of functions. Note that the int type is a base type, whereas function type is a compound type, as we will illustrate using an example program in this language. This example defines a function that takes an integer x as an argument and returns x plus 1. The type of this expression is int arrow int. Then this function is applied to the integer 42, yielding the integer 43.
Of this program is 20, which has the type int. The third program is not typeable as it violates a requirement of function calls, namely that the first expression in the pair must be a function, whereas here it is an integer 42. The next program is a bit trickier. It takes an integer x and returns a function that takes a number and adds it to x. So the type for the whole expression is the compound type int arrow int, where we put parentheses around the latter two ints to disambiguate the type. Putting parentheses around the first two ints would be the type of a function which takes a function from int to int and returns an int. The last program is not typeable as it violates the requirement of the plus operation, namely that both its operands be integers, whereas here one of the operands is a function.
If you have studied formal logic, you may be familiar with logical implications, if-then statements. Inference rules in type systems are if-then statements, which are used to reason about the types of program fragments, such as variables, expressions, and functions. An inference rule takes the form, if hypothesis is true, then conclusion is true, where the hypothesis and the conclusion are logical formulas. An example of an inference rule that might be used in a type system is if E1 is an int and E2 is a double, then E1 times E2 is a double. Now let's start developing a standard notation for expressing inference rules. To build this notation, we'll begin with a few small building blocks and then gradually add features as needed. The building blocks we will use are the inverted V to represent the logical AND operation, also called the conjunction operator. The rightward pointing arrow to represent logical implication, that is, the if-then operation. And the expression x:(t) to represent the statement x has type t. When reading logical formulas aloud, the inverted V can be read as the word AND the arrow symbol can be read as the word implies. Let's see how we can express the following English sentence in our notation for inference rules. If E1 has type int and E2 has type int, then E1 plus E2 has type int. First, we can group the first two type declarations together with an inverted V to represent their conjunction by the logical AND. Then, we can replace the if x then y construction with x arrow y, where X is the conjoined hypothesis and Y is the conclusion E1 plus E2 has type int. Finally, we can replace the phrase X has type int with the notation X colon int, giving us the following inference rule. E1 has type int and E2 has type int implies E1 plus E2 has type int. Observe that in this formulation of the statement, we have two separate hypotheses which have been conjoined to form a compound hypothesis. Each separate hypothesis must be true in order to guarantee that the conclusion is true. In general, inference rules have the form hypothesis 1 and hypothesis 2 and so forth up to hypothesis n implies conclusion. An inference rule may have an arbitrary but finite number of hypotheses that must be fulfilled to guarantee the conclusion. Traditionally, inference rules are written in the following way. Each inference rule has one conclusion and 0, 1 or more hypotheses. The hypotheses are considered to be conjoined, ANDed together. They must all be true in order to derive the conclusion. Inference rules without any hypotheses are called axioms. Their conclusions are statements we take to be fact without any preconditions. The hypotheses and conclusions all take the following form, where E is an expression and T is a type. This statement is called a type judgment. The pipe symbol followed by a hyphen is a symbol denoting the phrase, "It is provable that." Let's start building the type system for our example language by focusing on the rules for integers. The first rule we establish is that it is provable that I has type int for all literal integers I. For example, we could replace the letter I with 0, 1, 200, -3, etc. and the rule would still hold. Strictly speaking, we refer to such a template rule as a schema. And because there are no hypotheses in this rule, it is an axiom schema. We will name this schema int for future reference. The second rule we will establish is that if it is provable that E1 has type int and that E2 has type int, then it is provable that E1 plus E2 has type int. This is an inference rule schema as opposed to an axiom schema because there are more than 0 hypotheses. We will name this schema add. These rules thus serve as templates describing how to type integers and expressions containing the addition operator. By filling in or instantiating the templates, we can produce complete typings for expressions. Note that while hypotheses state facts about sub-expressions, conclusions state facts about the entire expression. Here's an example of a type derivation for typing the expression 1 plus 2. We first instantiate the axiom schema int by filling in the number 1 for I to produce the axiom, "It is provable that 1 has type int." Similarly, we instantiate the int axiom schema again to produce the axiom, "It is provable that 2 has type int." Then we can take these two conclusions and plug them in as hypotheses for the inference rule schema add. Because it is provable that 1 has type int and 2 has type int, it is provable that 1 plus 2 has type int. This conclusion completes the derivation of the typing for the expression 1 plus 2. We have discussed typing for integer expressions, which in our simple language are restricted to sums. Using the rules we have established so far, we can derive a rule such as this one. If it is provable that E has type int, then it is provable that E plus E has type int. This schema carries the type information for E in its hypotheses. Now, We also want to apply typing rules for variables. However, if we try to axiomatically define x's type, we find that the axiom has no way of carrying the type information for x, and we don't want to impose a rule that all variables must be of a single type. Moreover, we can't provide type information via hypotheses because these hypotheses must eventually be derived from axiomatic statements. So, we have run into a problem. How can we provide appropriate type information for a variable? The solution for a type system is to add more information to the rules. We can use an environment to give type information to free variables such as x in the rule var. A variable is free in an expression if it is not defined within the expression itself. In contrast, a variable that is defined in an expression is called a bound variable. For example, consider the expression lambda x is of type int yields x plus y. Variable y is free in this expression, but variable x is bound. In a type system, an environment is a function which maps variables to types. For example, if we declare the variable x to be an int in a Java program, the environment would map the variable x to the type int. The concept of an environment is general. In other kinds of static analyses, environments may map variables to other abstract values instead of types. Let's use the letter A to represent our environment, that is, a function from variables to types. We will use the notation A pipe hyphen E colon T to mean under the assumption that variables have the types given by A, it is provable that expression E has type T. Let's modify our previous rules int and add to include the type environment before the pipe hyphen symbol. And now we can write new rules, such as the axiom schema for typing variables, which we call schema var. Under environment A, it is provable that x has type A of x. A of x refers to the type assigned to x under the environment mapping A. A of x refers to the type assigned to x under the environment mapping A. Now we can make the last of the inference rule schemas for our language. We need to introduce rules for typing function definitions and function calls. For function definitions, we make the following rule, which we call def. Using our environment A, if it is provable that E is of type T prime, then it is provable that the function lambda x of type T yields E is a function of type T arrow T prime. Except we have a problem. In this expression, x is a free variable and we need its type. We can fix this by explicitly requiring the environment to map x to type T. We do so by adding the notation x arrow T in brackets besides the letter A in the hypothesis of this rule. Notice that this environment is the same as that in the conclusion of the rule, except that the environment in the conclusion of the rule does not give the type of x. This is correct since x is not a free variable in this expression. It is bound or defined as the argument of this function. Finally, we define the inference rule schema call to give type information for applications of functions to other expressions. If under the environment A, it is provable that E1 has type t1 arrow t2 and e2 has type t1, then it is provable that the result of calling e1 with argument e2 has type t2. This concludes the set of schemas we need in order to completely type our example Lambda Calculus language. Notice that there is exactly one schema for each of the 5 syntactic expression forms in this language. Now let's look at how we would derive the typing for a non-trivial expression using these 5 schemas. Later, we will see how to algorithmically compute these derivations. But let's work through some by hand first to get a feel for them. A type derivation is a procedure which allows us to derive the type of a program if one exists. The goal of the derivation is to show that an expression has a given type, derived ultimately from axiomatic statements. That is, there are no infinite or cyclic chains of hypotheses needed to show that some statement is true. Here, we will use our 5 schemas to derive the type of the program. Lambda x of type int yields x plus 1 applied to 42. See the lecture handout for a list of all the schemas for this language. We will work from the bottom up, checking to ensure that each step of derivation fits the template for one of the schemas we previously defined. The call rule schema requires that if applying expression E1 to expression E2 yields type T2, then expression E2 must be of type T1, and expression E1 must be a function mapping T1 to T2. In this case, the lambda expression plays the role of expression T1. The number 42 plays the role of expression E2, and T1 and T2 are both the int type. The call rule schema is therefore satisfied. Notice that we maintain an empty environment for this template. There are no variables mapped to types. We use an empty array to represent this environment with no such mappings. Now let's derive the types of the hypotheses of the call rule. The int axiom schema allows us to assert that the literal 42 has type int without requiring any further hypotheses. If we look at the first hypothesis of the call rule, we see we have a function definition. We therefore check to see that the def rule schema can be applied to this definition. This schema requires that if the conclusion is a function mapping a variable x of type t1 to an expression of type t2, then the hypothesis must be that it is provable that the output expression is of type t2 under the same environment with a single additional mapping of the variable x to type t1. In this case, notice that the environment in the conclusion is empty, and the environment in the hypothesis maps the variable x to the type int. Under this assumption, the hypothesis states that it is provable x plus 1, the expression that the function outputs, is an int. Therefore, the def rule schema is correctly instantiated to prove that x plus 1 has type int under the environment where x is mapped to type int. X plus 1 is an addition expression, so we now check that the add rule schema holds. Add requires that the hypotheses and conclusion have the same environment, that the expression in the conclusion have type int, and that it be provable the expressions in the hypotheses also have type int. The schema has been correctly filled in, so now we must verify that each of the hypotheses are provable. Like before, we have the int axiom schema, under which the literal 1 is provable to be an int regardless of the environment. It is not a problem that x is in the environment but doesn't appear in the expression. We may still conclude that 1 is provably of type int. We therefore focus on the last unproven statement. It is provable that x is of type int. under the environment where x is mapped to type int. However, we have a different axiom schema, var, under which we may prove that a variable has type t under the environment where that variable is mapped to type t. Because the var axiom schema may be instantiated by filling in t by the type int, the statement that x has type int is provable. We are now done. All sub-expressions of the entire program have been shown to be provable from axioms, leaving no unproven hypotheses. Therefore, we have completed the derivation and proven that the full program has type int. We are now done with the notation for type systems. Next, we will see some properties of type systems, such as what guarantees we have if a program type checks. That is, it is successfully typed according to the axiom and inference rule schemas versus if the program does not. And an algorithm to mechanically compute a type derivation if it exists. Let's return to our Java example from the beginning of this module. In this case, the function f checks whether the variable a evaluates to true, and if so, then it returns b, otherwise it returns c. Our Lambda Calculus language from earlier currently does not have the capacity to directly express this behavior. So let us extend the language to allow if-then-else statements. We'll need to add a new inference rule schema to check that if-then-else statements are correctly typed. The rule we'll add, which we'll call if-then-else, has 4 hypotheses. If under the environment A, it is provable that E0 has type bool, E1 has type T1, E2 has type T2, and T1 equals T2, then it is provable that the expression if E0 then E1 else E2 has type T1. Note that we are implicitly introducing a new type to our language, the bool type. We won't formally add all the required schemas to type Boolean expressions in our language, but you can try writing these rules yourself as an exercise. For the purposes of this module, we will assume Boolean expressions to be fully typed going forward. Also, notice we have a new form of hypothesis, T1 equals T2, which we do not preface with the is provable that notation. This expression is called a side condition. It is an additional constraint that must be satisfied in order for the inference rule schema to be instantiated. We'll use this rule several times throughout the remainder of this module to illustrate some key concepts. If we can successfully type the if-then-else statement, then the first hypothesis in the rule guarantees that E0 will be a Boolean. The latter hypothesis and side condition guarantee that E1 and E2 will be of the same type. These sorts of guarantees are characteristic of sound type systems. Formally, we define a type system to be sound if and only if, whenever it is provable under an environment A that E has type T, and furthermore, whenever an environment A maps variable x to type T prime, then x has a value in that type T prime, then E always evaluates to some value V in T. Sound analyses are extremely useful. If a program type checks according to a sound type system, then no errors of the kind checked by the type system can arise in any execution of the program. We say that a sound analysis verifies the absence of a class of errors. This is a very strong guarantee. The property verified holds in all executions of the program. This guarantee is encapsulated by Robin Milner's classic slogan, "Well-typed programs cannot go wrong." But soundness comes at a price. Because of the undecidability of static analysis, a sound analysis that always terminates must occasionally generate spurious errors or warnings, that is, false positives, due to the abstraction the analysis makes. This means that the sound analysis is incomplete. An alternative approach is to use an unsound analysis, which allows us more control over the false positive rate. However, unsound analyses have the possibility of failing to detect errors, that is, producing false negatives. Type systems are sound analyses. While they may generate false positives on occasion, they will never produce a false negative. But most kinds of analyses for detecting bugs, so-called bug finding analyses, are not sound. You can learn more about these kinds of analyses for Java and C by following the links in the lecture handout.
Ints and returning an int, while the second Boolean expression would output a function mapping ints to ints, and so the resulting function application would also be well defined. This gives us two examples, two false positives, where our type system is overly conservative about what it considers to be a valid program. While our type system can be proven to be sound, we will never be without these false positives, even if we try to introduce new rules allowing us to detect whether the then or else branches of Boolean expressions are followed.
Let's look some more at the notion of side conditions. These conditions occur in many type-based analyses. They are constraints that must be solved, that is, satisfied, in order to verify that the inference rule is properly applied. Checking whether these side constraints can be solved is a separate algorithmic problem that we will cover shortly. For example, consider the program if a greater than 1, then lambda x of type int yields x, else 10. In an environment where a is of type int, expression e1 in this program has type int arrow int, while expression e2 has type int. Without the side condition, this program would be typed as a function mapping ints to ints. This would cause the type system to be unsound, as the program would not evaluate to a correct type if a were ever less than or equal to 1. Another example of where side conditions occur are with recursive functions, functions which call themselves in their own definition. The constraint that must be satisfied is that if x is of type t1 and e is of type t2, then t2 equals t1. In fact, this is a bit too strict. It could be relaxed to requiring only that t2 is a subset of t1. Recursive functions yield constraints that are themselves recursive. The same holds for loops. We observed this phenomenon in the module on data flow analysis, wherein loops in programs necessitate multiple iterations of the chaotic iteration algorithm. That algorithm in reality is solving a system of recursive constraints, namely data flow constraints for computing the in sets and the out sets of data flow facts at each program point. In general, the difficulty of solving constraints depends on the language of the constraints and the details of the application. Another important property of type systems is that they do not require types for entire programs, and for good reason. The goal is to alleviate the annotation burden on the programmer by reducing verbosity. The problem of determining the type of the entire program, if it has one, is called type inference. Since some types are usually specified in elements such as variable declarations and function signatures, type inference is also called type checking or type reconstruction. Type inference is a challenging problem for complex type systems such as Haskell's, and for tricky languages such as JavaScript. Not surprisingly, akin to any software analysis, there are many trade-offs that a type inference algorithm has to strike in aspects such as soundness, completeness, efficiency, and automation. Let's look at the outline of a type inference algorithm. The algorithm uses constraints to uniformly solve both the problems we just discussed: how to check side conditions arising in type rules, and how to infer the type of the entire program if one exists. As we learnt in the module on constraint-based analysis, this algorithm involves two steps. First, collect constraints based on the type rules. Once we have generated a set of constraints, we solve them using a simple but powerful algorithm called unification. Unification is highly efficient and runs in approximately linear time in the size of the input program. If the constraints can be solved, the solution will provide types for each program fragment, which in the case of a Lambda Calculus language is each variable and each expression. If the constraints are unsatisfiable, there is a type error and the program is not typeable. For richer type systems, constraint-based type inference might use an off-the-shelf automated theorem prover or even an interactive theorem prover. However, for this type system, we will illustrate the constraint solving process using the unification algorithm through a series of examples. Throughout these examples, we will denote type of as double square brackets. Suppose we would like to infer the type of the program shown here. Let's start out with the expression x plus y highlighted here. From the type rule for addition, we know that the types of sub-expressions x and y must be int. And furthermore, that the type of the expression x plus y must also be int. Likewise, by the type rule for function definitions, we can conclude that the type of the function highlighted in blue must be equal to type of the parameter y, arrow, the type of the body x plus y. Lastly, we generate constraints for the type of the entire program. Again, we use the type rule for function definitions. Now that we have generated all the constraints, we proceed to step 2, solving them using the unification algorithm. Informally, at each step of the unification algorithm, we simply pick a substitution from a constraint and apply it to all the remaining constraints. The goal is to attempt to unify the two terms in each constraint. That is, to make them identical by applying a substitution. For example, constraint 1, type of x equals int, would substitute int wherever type of x appears in the remaining constraints. If a contradiction arises during this process, then the program cannot be typed. If no contradiction arises, then the substitution will have given us the type of each program part, including the type of the entire program. We will illustrate the unification algorithm by applying substitution type of x equals int from constraint 1 to the remaining constraints. This simplifies constraint 5 to this. Marching ahead, we next apply the substitution from constraint 2 to all the remaining constraints. Type of y only occurs in constraint 4. So, we substitute int for type of y in constraint 4 to obtain this. Next, we apply the substitution from constraint 3. Again, type of x plus y only occurs in constraint 4. So, we substitute it by int to obtain this. Now, we choose constraint 4 for substitution. The left-hand side of constraint 4 occurs in constraint 5. So we substitute it with int arrow int to obtain this. This substitution has given us the type of the entire program, int arrow int. It is a function which takes an int and returns a function that takes an int and returns an int. In summary, we were able to successfully solve the constraints and infer the type of each program part. Now let's look at an example where type inference fails. That is, the program is untypable. Consider the following program. As before, we generate constraints for each program part using our previously defined type rules. Our type rule for integer constants gives us types for the constants 42 and 5. Now we generate the constraints for the expression x plus 5. From the type rule for addition, we conclude that the type of sub-expressions x and 5 must be int. We already have a constraint stating that the type of 5 must be int. So we only add the constraint stating that the type of x must be int. Furthermore, the type rule states that the type of the expression x plus 5 must be int. Next, we generate the constraints for the highlighted function. By the type rule for function definitions, we know that the type must be equal to a function type from the type of the parameter to the type of the body. Lastly, we use the type rule for function calls to obtain the constraint on the type of the entire program, namely that the type of the called function 42 should be a function type from the type of the argument, which is itself a function, to the return result, which is the entire program. Clearly, we can see that this cannot possibly be the case, since the type of 42 cannot simultaneously be an integer as dictated by constraint 1 and a function as dictated by constraint 6. Nevertheless, let's continue with the unification algorithm to see where this contradiction arises. First, we select constraint 1 and substitute int for type of 42 in constraint 6 to obtain this. Similarly, we select constraint 3 for substitution in constraint 5 to obtain this. Next, we select constraint 4 for substitution. Type of x plus y only exists in constraint 5. So we perform the substitution to int there. Lastly, we use constraint 5 to substitute the type of the highlighted function in constraint 6. Here, a contradiction arises. It cannot be possible for an int to equal a function type. Thus, unification has failed and this program is untypable as expected. Earlier in this module, we promised that type notation would be useful in contexts aside from type systems. Indeed, they are useful for describing a wide range of static analyses. Instead of speaking in the language of types, we can interpret each part of a rule of inference in a different way. We will use E to represent the program or program fragment to be analyzed. T will represent an abstract value which need not necessarily be a type, computed for the program E. Instead of mapping variables to types, the environment A may now describe assumptions needed for aspects of E that are determined by the rest of the program. This will allow us to recursively analyze hypotheses of each inference rule, sub-expressions of the program, to prove that the program has some particular global property. What sort of properties can we reason about in this manner? As a starting example, let's use type notation to determine the sign of a numeric computation. For example, we would like to prove that the output of -3 times 4 is negative. Abstracting this particular computation, we can represent it as negative times positive equals negative. The abstract values that we will use in this analysis are plus, representing the set of all positive integers, 0, representing the set consisting of just the integer 0, and minus, representing the set of all negative integers. The environment in this system will be a mapping from variables to one of these three abstract values. So far, we have described rules for deriving the sign of the product of two expressions. However, what if we want to describe the sign of the sum of two expressions? Let's add the following rule. Under environment A, if it is provable that E1 has value plus and E2 has value minus, then it is provable under A that E1 plus E2 has value what? We have a problem here. We don't have an abstract value that covers this case. How do we solve this problem? The solution is to add new abstract values to our system to make sure the system is closed under all operations. There are no expressions with undefined abstract values. To our existing abstract values, we will add two additional abstract values. Top, which will represent the set of all integers, and bot, which will represent the empty set. Notice that the abstract values no longer represent disjoint sets of concrete values. This is okay. This happens quite regularly in abstract domains, as we saw in the module on data flow analysis and earlier in the module on Introduction to Software Analysis. Backtracking a bit, let's return to our analysis of the if-then-else expression from our Lambda Calculus language. It may seem like a digression from our current topic, but it will wrap back up nicely. Recall that in our algorithm's examination of the if-then-else expression, each of the sub-expressions were analyzed independently of one another. It didn't take into account the order in which the expressions were listed. It only checked that E0, E1, and E2 were of the appropriate types. We could have swapped E1 and E2 and the analysis would be unaffected. This is called flow insensitive analysis, which you may recall from our study of pointer analysis. The analysis is independent of the order in which the statements appear in the program. In effect, it treats the program as a set of statements with little other structure imposed. In practice, you'll find that most type systems are flow insensitive. The reason for disregarding the control flow of the program is the usual reason for abstraction in static analysis. It simplifies the representation of the program state that our algorithm operates on. In particular, there is no need for modeling a separate state for each sub-expression. The resulting analyses are efficient and scalable, allowing them to be used liberally in many applications. The trade-off is loss of precision, the usual trade-off for speed in static analysis. To attain a faster sound type system, we necessarily end up generating more false positives. Indeed, we have a constant time type checking algorithm that's perfectly sound. Just reject all programs. But of course, such a scheme, while fast and sound, is completely useless. If we are willing to sacrifice simplicity and efficiency in order to increase our precision, we can make our abstraction of the program state more realistic. One way to do so is to remain sensitive to control flow. In this case, each statement has an input environment and an output environment, and we order the analysis of sub-expressions by the environments that are produced. Therefore, the result of the analysis now depends on the order of the statements, allowing us to make a finer distinction between correctly typed and incorrectly typed statements. In the if-then-else schema example, we would start by proving that under environment A, E0 is a bool and then output a new environment A0. This environment then flows into the analysis of both the statement that E1 is of type T1 and that E2 is of type T2, each of which produce their own output environments A1 and A2. We would then need to solve the side condition that environments A1 and A2 are equal, in addition to the previous side condition that T1 equals T2. In order to prove that under the environment A, the expression if E0 then E1 else E2 has type T1 and output environment A1. This kind of analysis is called flow-sensitive analysis. The analysis result depends on the order of statements in the program. Now is where we start tying together our previous thread on different types of static analyses with this thread. The input and output environments in this kind of static analysis should remind you of something we saw earlier. In data flow analysis, we had in and out sets of program facts. These sets would play the part of the input and output environments. Therefore, data flow analysis, as we might expect from its name, is a flow-sensitive static analysis, which could be represented using type system-like notation. The environments shown previously in flow-sensitive analysis were fairly abstract. Let's look at a more concrete example by extending our rule of signs system with assignment statements. We add the following inference rule schema. Under environment A, if it is provable that E has value plus and results in environment A, then under environment A, it is provable that X assigned the expression E results in the environment A modified so that A maps X to the value plus. As we alluded to earlier, flow-sensitive analysis can be expensive. Our abstraction is more complex. Each statement has to maintain its own separate model of the program state. Because we are keeping track of more information, we end up with a polynomial increase in cost over flow-insensitive analyses. We can further refine our model of the program state in order to improve the precision of our analysis. Recall that for the statement if E0 then E1 else E2, our analysis doesn't consider whether E0 is true or false. This leads to situations where unreachable code, that is, if E0 is always true or always false, can cause the program to fail to type check, or to a situation where the type system rejects a program that would have ill-defined behavior on a path that is logically impossible to take through the code. Recall that we saw both of these situations in a previous quiz. We call this sort of analysis path insensitive, as it does not consider whether certain paths through the code are impossible to take. It rejects a program that has a bad path, even if this path can never be taken, yielding false positives in the process. By making our analysis sensitive to program paths, we are able to eliminate this form of false positive at the cost of more complexity in our program abstraction. To do so, we augment our environment for each statement with a Boolean predicate P. If P is the predicate under which an if-then-else statement would be executed, then we add P to the input environment of the first hypothesis that E0 is a bool. For the second hypothesis that E1 has type T1, we add P conjoined with E0 to the input environment. And for the third hypothesis that E2 has type T2, we add P conjoined with the negation of E0 to the input environment. Note that we are still retaining the distinction between input and output environments for all the hypotheses. If P is the predicate under which an if-then-else statement would be executed, then we add P to the input environment of the first hypothesis that E0 is a bool. For the second hypothesis that E1 has type T1, we add P conjoined with E0 to the input environment. And for the third hypothesis that E2 has type T2, we add P conjoined with the negation of E0 to the input environment. Note that we are still retaining the distinction between input and output environments for all the hypotheses. Additionally, we no longer solve the side constraint that the output environments A1 and A2 are equal. Instead, the conclusion allows for either of these to be its output environment based on the truth value of E0. Symbolic execution, which we will study later, is an example of a path-sensitive analysis. Note that path-sensitive analyses are also flow-sensitive, as we preserve the input-output environment ordering. As you might imagine, keeping track of these different execution paths can be quite expensive. In the general case, there can be an exponential number of paths to track compared to the number of statements in the program. But this complexity appears to be a necessary evil in many different applications. Path-sensitive analyses are often performed using backtracking instead of explicitly merging environments together. A single path is explored until termination, and then the analysis backtracks to a decision point before exploring another path. This allows clients to prioritize the exploration of paths that are potentially more interesting than others. For instance, in the case of a bug finding tool, paths that are more likely to expose a bug.
Does not have any locking errors, certainly requires at least flow sensitivity to detect that any lock acquisition comes before lock release. However, just flow sensitivity is not sufficient in this case, as it is too weak to recognize that if z greater than 0, the then portion of both branch points must be taken. Path-sensitive analysis would be able to recognize this fact. So path-sensitive analysis is able to prove that the program does not have any locking errors.
We have discussed different kinds of analyses and their abilities to detect errors in programs with different structures. While we have used the notation and terminology of type systems in this discussion, the typical applications of these analyses often have different names and purposes in practical applications. While it is certainly possible to create a type system that is flow sensitive or even path sensitive, we normally think of type systems as flow insensitive analyses. Flow sensitive analyses are usually associated with data flow analyses, and symbolic execution is a prototypical path sensitive analysis. However, these lines have become more blurred lately. For example, in the research literature, it is not uncommon to come across flow sensitive type systems and path sensitive data flow analysis. This concludes our introduction to type systems and their usefulness to software analysis in general. In this module, we have learned what a type is, an abstract value consisting of a set of concrete values having that type. How to compute the types of programs using derivations from type rules. The properties of type systems: soundness, that is guaranteeing no false negatives; incompleteness, that is the occurrence of false positives; and type inference, also called type checking or type reconstruction. How to describe other kinds of static analyses using the notation of type systems, and the strengths and costs of flow insensitive, flow sensitive, and path sensitive analyses. We have only scratched the surface of type systems in this module. The study of type systems remains an active area of research with many fruitful results. We have included a list of resources in the lecture handout for further reading on topics in type systems.